I'll be talking about integrating electric vehicles and the electricity grid. So I just wanted to give kind of a high-level overview of some of the topics and issues that are arising in the space, and show some of the projects that we've been working on related to this integration. So to provide a little bit of motivation, electric vehicles, as I'm sure most folks are at least somewhat familiar with, have been growing fairly rapidly over the last decade since they were first introduced. So on the chart on the left, you can see a fairly sort of substantial growth year over year. There are a couple of years where the growth has been a little bit flat, but usually it's picked up again, and 2020 and 2021, I think that there are expectations for it to continue on its upward trends. And I think this is motivated by the fact that that there's a lot of movement both in the industry side as well as the policy side to promote these. So you may have seen some recent headlines, banning gasoline cars by 2030, by 2035. All of the hubbub around President Biden's new American Jobs Plan includes a huge amount of funding specifically dedicated to supporting electric vehicle adoption and electric vehicle infrastructure. And there are a lot of sort of continuing announcements by automakers. It's hard to keep track sometimes. So all of this is kind of pointing to the fact that this new technology is likely going to have a pretty important impact on both the transportation sector as well as the electricity sector. So the chart on the left is this Gantt chart that I believe Sandia puts together every year. And it shows basically going from primary energy to end use energy. And one of the things that you can see is the transportation sector here and its relation to electricity generation is fairly small. Most of the energy is coming from your primary source of petroleum. And as electric vehicles begin to shift more and more towards, as transportation in general begins to shift more towards electrification, that portion is going to grow substantially. And so that's going to mean some important integration between these two sectors. One of the things that sort of really motivates a lot of the research questions that I've worked on is thinking about emissions associated with this technology switch. And so when we break down emissions by sector, you can see transportation and electricity are two of the largest emitters, and actually transportation overtook electricity just in the recent past. But as electrification happens, I think there's going to be, somewhat of a blending between these sectors, because now they're going to be essentially the same thing. When we think about emissions coming from gasoline vehicles, so I'm not going to say it's super easy, but it is definitely a little bit more straightforward. When you think about accounting coming from fuel use. When we talk about emissions coming from electric vehicles, you can see that the process is a little bit less straightforward. You are getting electricity from your power grid system, and you have to essentially figure out a way of essentially estimating where that electricity comes from and what are the impacts associated with generation of that electricity. And so like I was mentioning before, a lot of my work is going to be sort of centered around looking at emissions. But as you can see here, there are a lot of interesting potential interactions between the electricity grid and the transport sector now that you have this bridge through electric vehicles. And so we're going to talk a little bit about some of these interactions through some of the projects that we've done as well. So I'm going to kind of highlight a couple projects again, going from a sort of small scale, localized type of effects up to sort of large scale, statewide or nationwide accounting for effects with this integration. So the first project that I'll highlight is looking at charging load effects on distribution infrastructure, specifically in California, and actually more specifically in PG&E service territories. So when we think about the distribution, local infrastructure, these are things like substations, distribution lines, local transformers. And so one of my students who I guess now is officially Ag alum is responsible for a lot of the work in this project, Jake Heileman. And so this is some of the stuff that he's worked on, or he had worked on during his time as a master's in Ag. This is a map of PG&E's distribution system. You can see sort of feeder circuits highlighted by the colors, as well as substation locations that are seen in sort of black dots. And to give you maybe a better sense of what this looks like, I can kind of zoom in on this example network in Davis. And so you can see that from a single sort of distribution network coming out of this substation, which some of you guys may be familiar with over on, I believe it's on Third and L. You can see that there are a number of distribution feeder lines. And as part of the data set that was collected, we also have a view of a localized load demand. So this is electricity loads coming from all sorts of electricity use, both residential, commercial, industrial, and even agricultural. And these represent daily representative highs and lows in each corresponding month of the year. And so from here, we can look at attributes of specific distribution network infrastructure. And what we can do is look at projections of electric vehicle adoption. And so I won't get into all the details of the modeling, but essentially the sort of outcome is being able to do these simulations where we can look at how electric vehicles will contribute to existing load curves. And what that means for impacting the distribution infrastructure. There are lots of sort of different types of ways that you can affect infrastructure. There's capacity on the lines, capacity of the transformers, things about affecting the lifetime based off of the usage profiles of transformers. And so we've looked at these sort of load thresholds that you can see in this blue line, and whether or not adding electric vehicle charging will ever sort of exceed these thresholds, which often means that you need to think about transformer and localized upgrades. And so, you know, at a higher level, we can sort of go through all of the feeder networks on PG&E and do these sort of simulations to figure out, okay, at what point and at how often are you sort of aligning with peak loads, and which substations and transformers will actually reach their threshold capacities and require upgrades. And so this is a chart showing all of the feeders in the East Bay within PG&E across different sort of scenarios of electric vehicle adoption, and showing essentially which feeders will be exceeding their thresholds, but also looking at what sort of percentage of these feeders will have sort of higher and higher intensities with their coincident peak. Okay, so that's one project that was done by an ex students and sort of really highlight some of the localized issues that have to do with integration with the grid. The next project that I'll talk about is thinking about environmental impacts of extreme fast charging. So this was work that we did with the US EPA, I think 2 years ago, thinking about a particular type of future of electric vehicle refueling. And so I wanted to sort of introduce this concept to folks who are unfamiliar. There's a type of charger which we classify as sort of an extreme fast charger. These are at 350 kilowatts, which is extremely high power rating. So what most people consider to be, we call a DC fast charger today, usually operates between 50 to 150 kilowatts. But the 350 kilowatt system is meant to act as a replacement, a sort of more direct substitute for, filling up with gasoline. And so these chargers can fill an entire battery charge on the order of about 10 minutes or so. And so this is a very sort of high power demand, and also has sort of implications on how it's going to interact with the electricity grid. It actually will have sort of in relation to the work that I was showing before, substantial impacts on the distribution infrastructure. But actually the work that we did in this project was thinking more at a high level, in aggregate, how it would change charging load shapes, and therefore the corresponding response for power generation at the wholesale and transmission level. That was sort of more of what we were focused on in this study. So what we were able to do here was to look at a diversity of different charging loads with a whole bunch of scenarios based off of how people would be using extreme fast chargers in comparison to how folks are charging today. And so we looked at certain types of loads that would also be influenced by, if you were a station owner of an extreme fast charging station, you could also partake in load management activities that would focus on maximizing your profit and reducing things like peak pricing and I'm totally forgetting the term right now, when you're getting priced off of the power rather than the energy. And so in order to estimate the emissions responses, we actually simulate the operation of the entire US electricity grid using an economic dispatch models that were developed in-house. And so this is an overview of all of the power plants in the country. And what we're able to do is actually figure out essentially which power plants are responding to specific vehicle charging events, and therefore allow us to examine the emissions impacts upstream of all of these different sort of charging profiles. So this is one example of a scenario of lots of extreme fast charging, and which power generation units are responding to them, as well as the corresponding emissions within each of these sort of balancing areas. Okay, so I think another sort of hot topic is thinking about electric vehicle emissions implications, especially at the sort of scale of thinking about climate change mitigation. And so recently, the University of California's Institute of Transportation Studies just released a report looking at decarbonizing all transport by 2045. And so this was work done for the California EPA. I had a small role in this project looking at emissions associated with electric vehicles. And I think that when you look at the sort of broad scope of I would say at least famous studies for electric vehicle emissions, a lot of them are focused on these high resolution examinations of emissions today. And I think that's that thinking about the dynamics of the grid is really important for characterizing the potential for emissions reduction. And so it's a little bit of a harder problem, because you have to think about not only how electric vehicles are being adopted, but also how the grid is changing. And so in this case study, specifically in California, we were both looking at these grid changes as well as adoption of electric vehicles. And it's an interesting problem because you have sort of directly conflicting trajectories for what it means for emissions in totality, because as you have more electric vehicles, the emissions associated with those cumulative electric vehicles is going to increase. But at the same time, if your grid is getting cleaner, then the total will also decrease due to lower emission rates on the grid side. And so this is sort of one set of results and scenarios that we looked at to address this particular issue. So will electric vehicles reduce transport emissions? Yeah, I think that's one of the sort of big takeaways, is that when we look at the cumulative emissions from passenger transport over the next several decades, the sort of biggest drop that we can achieve is through electrification. And so there are lots of extra things that you can do in terms of cleaning the grid, in terms of like doing smart charging and managing charging in certain ways. But you can see here that those marginal benefits in cleaning the grid and doing things like smart charging are sort of incremental improvements in comparison to sort of just electrifying vehicles in general, because they're so much lower in emissions than existing gasoline vehicles. Okay, and so I wanted to show one last project. This is a sort of more fantastical type of examination of a future scenario. So this was work that we did with Lawrence Berkeley National Lab to look at a potential future where all vehicles are sort of fully shared, autonomous, and electrified in such a way that you could really sort of completely transform the transport sector. And then sort of my contribution to this work was really thinking about what that would mean for the grid. And so here, this is a set of scenarios where we were looking at different fractions of smart charging, and then different fractions of a sort of totally privately owned electric vehicle fleet versus a 100% shared autonomous fleet. And you can see that both the added flexibility of smart charging as well as the changing to a shared fleet lead to really different load profiles. So these are charging load profiles over a 3-day period on the grid. And this ultimately leads to sort of really widespread impacts in the transportation system and in the electricity system. There are a lot of interesting, I don't want to spend too much time on this figure, but there are a lot of interesting sort of punchlines here that as you do this sort of transition, it has really large effects on the fleet size. So, we can go all the way from 150 million vehicles down to something like 10 million vehicles and still maintain or fulfill the same amount of demand. The peak power demand will decrease a lot, and the emissions will also be greatly affected. Yeah, okay, and so hopefully this highlight is a nice sort of quick examination of a lot of interesting topics in the integration of electric vehicles and the grid. I think one of the really nice things in working on a lot of these projects with a lot of different partnerships is that there's a huge amount of interdisciplinary cooperation, which is, I think, kind of really necessary in this field. So, I've worked with power systems folks, economists, transportation behavioral researchers, public policy wonks, the whole sort of gamut. And then the other thing that I would say, if I had more time to highlight is that I think that a lot of this stuff is a really hot topic in the policy world right now. There are a lot of opportunities and challenges to deal with in thinking about growing electrified transportation. Yeah, and so hopefully this is all sort of interesting for you folks, and happy to take any questions or comments.
Great, thanks so much, Alan. If you have questions, we got claps going for you. If you got a question, feel free to raise your hand. Greg, you are up. Feel free to unmute and you can ask your question virtually in person.
Hey, Alan. Yeah, I had a quick question about something on slide 18, which was you were showing the emissions, future emissions from regular charging and smart charging, and it looked like, yeah, around 2040 that smart charging emissions were actually higher than conventional charging. Can you explain what's going on there?
Yeah, it actually has to do with the grid mix. So the electricity grid is actually slightly different in these two scenarios because of the way they get deployed to meet the different demand profiles. So it just happens that because of the way the model does the capacity expansion, you end up with slightly higher emissions in the smart charging case. Yeah, it was kind of a weird finding for us as well.
Okay, thank you.
Yep. And I actually see a question in the chat, what grid emission data was used in the studies? So it's a variety of sources. For a lot of the in-house grid development models, we were using sources from EPA, from IPM needs modeling, as well as eGrid data.
Okay, yes, this is Subhrajit here. I was curious, were you using marginal emissions when you are thinking of adding electric vehicles to the grid?
Yeah, so this is, I would classify as like consequential. So we're not doing marginal emissions in the sense that like you're doing a lot of what you see in the literature where you do regression based modeling and looking at what happens when you add incremental load. This is actually simulating the operation of the generators. So what we do is we run the model with and without the charging load, and then we figure out which power plants are responding to the load, and then we use those to calculate the emissions. I think that this type of method is going to be a lot more robust than doing a regression-based marginal emissions approach when you're talking about future emissions, because you've got a changing grid fleet, as well as once you have enough volume of electric vehicles, you're not going to be on the margin anymore, because you could actually change the dispatch, right, of your generators.
Cool, thanks. And on slide 19, could you explain those two colors?
Yeah, so this is like all passenger transport from 2020 through 2045. And so you have gasoline cars in green, and then electric vehicles in red. And the reason why you still have, even in like 100% electric vehicle case, you still have gasoline emissions, it's because it's counting everything from now until you phase all the EVs out. So you're still getting gas emissions up to that point.
Thank you.
Great, thanks. We have time. If you have any more questions, let us know. We have time for maybe one more before we get started with Cori's. Well, Alan, I look forward to hearing the next. So we have we have smart charging, we have extreme fast charging. So I look forward to the next. You're gonna have to like up the wording. You're gonna have to have like
extremely smart charging.
Extremely smart charging, or like, right. Brilliant something. You'll need something next.
Yeah.
We'll really appreciate sharing this with the group. And if you're okay, I'll put your email in the chat.
Yep.
So if anyone wants to follow up with you, there's Alan's email. And with that, we will pass the slides over to Cori. Thanks, Alan.
Thanks, Alan. Welcome, everyone. I'm Cori Jackson with the California Lighting Technology Center, and I have my face up now, but my bandwidth is bad by default. So I'm going to turn off my video while I share my screen and go through a project that I've been working on. So this talk is about optimizing building operations, specifically commercial building operations. I think as I pull this up, in one of Alan's slides there, when he was showing electrification and transportation, buildings were a little bit smaller wedge of that pie, but I think I saw they still accounted for, maybe it was about 11 or 15% of all the emissions today. So buildings are an important topic when we think about energy savings and when we think about carbon emissions and reducing carbon emissions. But the project I'm going to talk about today is one where we are looking specifically at cost. And so here in California, soon, if some of you haven't already heard of this, we will have demand flexible standards, and buildings and appliances will be required at some level to respond to changing grid conditions. And one of the ways in which those changing grid conditions will be communicated to buildings and down to the subsystems at the building level is through pricing signals. And the idea is that we'll have real-time pricing that's going to vary dynamically. And so we want to have buildings out there that are able to respond. So this project really looks at capitalizing on those forthcoming real-time pricing signals and demand management standards, and how can building owners leverage that information and that variability to put some money back in their pockets. So one of the first things I want to talk about, essentially 3 parts to this talk. And if I can make the slide progress, there we go. I want to talk about, just as a basis, a little bit about mathematical optimization, and that's where my research starts from. And then we're going to talk about the fun stuff, which is how do we use that to do some model predictive control, or how do we optimize our building operations under those dynamic real-time conditions. And then at the end, we're going to present some preliminary case study work that we're doing to test the models and discuss the energy savings and the cost savings to building owners. So first, the background. So when it comes to mathematical optimization, really you can think about it as a broad class of problems that fundamentally all boil down to the idea of selecting an ideal element from a set of alternatives with some given set of constraints. So how do we make the best decision? That's always the question, especially when the choices may seem infinite. Often they're not infinite, they're just almost too large to comprehend. And so as these choices become very large, we have to think about how we might solve those kinds of problems in a more efficient way. And we have exhaustive search, right? So we could think if we had n objects, say, and we wanted to maybe find the shortest distance between n, let's call them cities. This is a classic combinatorial optimization problem, the traveling salesman problem, one of my favorites. If we had 20 cities and we wanted to find the shortest distance between 20 cities, it would be something like 20 factorial routes that we should look at before we can guarantee that we found the shortest one. And we can play some games. We can say, well, if you only have symmetric routes and you're visiting each city only once and you start from one, you can get it down to something like, you know, n-1 factorial divided by 2, something like that. But you're still a huge amount of options to consider, something like 10 to the 18 for 20 cities. And so we need a more subtle approach to these kinds of problems so that we can start reducing the necessary attempts to guarantee that we found our best solution. And that's where algorithms come into play. And for this discussion and my work in particular, I use the term solution and algorithm in very specific ways. So I want everyone to think about that in the same ways that I am as I'm talking about this work. An algorithm is going to find an exact solution. It's going to find an optimal solution, and that solution is going to be guaranteed and supported by mathematical proof that it's the very best choice you can make, or the very best option from that set of alternatives. When we are just thinking we want to get close enough, we can then talk about heuristics. And heuristics are sometimes good enough to give us an answer to a problem that will meet our needs. But if we want to talk about actually solving a problem and finding the optimal solution, then we're going to use an algorithm. And an algorithm, for example, with that traveling salesman problem, where we went from 10 to the 18, with an algorithm, we can get down to something like 10 to the 8 possible options to consider before we're guaranteed to find the best. So we're talking 10 orders of magnitude faster in terms of solving these kinds of problems. And so one of the tools that we have in our arsenal to think about these really large problems is linear programming. And as mathematicians and scientists and engineers, we love linear programs for a number of ways, a number of reasons. And linear programming is really just the mathematics of systems of inequalities. That's all it is. And they can be very large systems of inequalities. But overall, because they're linear, they can be solved more quickly than some other methods. And so we have linear programs out there or models out there that may have millions of decision variables, millions of variables to consider, millions of constraints to consider. And so we need an algorithm to reduce that problem down to something that's manageable, and manageable with today's modern computers. And so we have a number of those out there. There's not just one algorithm for any one problem. In linear programming, one of the most famous is the simplex algorithm developed by George Danzig. And so there's also the algorithm I showed on the previous slide with that reduced our running time down to 10 to the 8 was developed in '62 by Bell and Feldman and Camp, I believe. So we have all these tools out there, and what we want to do and what I'm working on is how do we take these tools that have been used for decades in places like finance and sports and all kinds of logistics problems. How do we take that and use it to really run a building better? And so before we dive into that, one last thing, these linear programs have a format. And so I'm going to use some of these terms. And when I do, know that they refer back to this general format of a linear program. And number one, so we have an objective function. And this is just a function that describes our objective of interest. So for my research, for this particular project, it's minimizing cost over time. We could have a maximization problem, maximizing daylight in a building, whatever the case may be. But whatever that objective function is, it's supported by a large system of constraints. So how can we use the resources, or how do we need to constrain this model to better mirror what we want to understand in the real world? And so again, these systems can have millions of decision variables and hundreds of thousands of constraints. And how do we take all of that information and use it to achieve something very practical? And so in the buildings world, across building science, this has been done in a number of different ways. And if you think about the building life cycle, you have design, you have construction, you have operation. And in each of those sort of building phases, people have used mathematical optimization to make better decisions. In the design phase, for example, architectural design optimization has been in use for several decades. And this is optimization of the design of the building based on fixed assumptions. So you might want to minimize truss weight or maximize daylight, as I mentioned before. When it comes to construction and commissioning, you'll have optimization and programs where you might want to optimize thermostat set points or schedules or other types of commissioning parameters for your building. But again, they're based on fixed assumptions. And so over time, we know that our assumptions are not ever correct usually. And so we really need to start thinking about how do we optimize based on real-time conditions. And this is where model predictive control comes into play. And this is an optimization technique that's really come into its own, I would say, in the last 10 years or so. And that's due to a couple of things, which I'll touch on in a minute. But model predictive control is essentially the periodic optimization of equipment or processes based on actual changing conditions. And so and I'll call it MPC for short, with predictive control, what you're doing is looking out over a time horizon, usually less than 12 hours for most MPC models, looking out over a time horizon and that predicting what the impacting variables will be in terms of, it might be weather, it might be electricity prices, which is what I'm looking at. It could be carbon emissions. And you're basing your control of the building or of a subsystem of the building on those predictions. And you're optimizing the system and you control your equipment for one or more time steps in your horizon. And then you re-optimize again as conditions are updated. So it's this sort of rolling time horizon approach where we're constantly looking ahead. and using information about the building and about what's going on in terms of its occupants and its operations to better schedule or better operate the energy consuming systems in the building. So model predictive control. So the things that I've been working on and we've been working on at CLTC and in collaboration with Kansas State University, which is also where I work, we've been looking at how do we use model predictive control to look at buildings as a whole system. Model predictive control has most typically been used in terms of individual systems, looking at how we optimize a heat pump, or how do we optimize a water heater to avoid, to reduce energy or to avoid carbon intensive energy times of the day. Just like Alan talked about, really the grid and the generation is a mix of different fuel types. So we could optimize our operations to only use energy when we're using renewable sources, for example, and reduce carbon emissions. But for this project, it comes down to one very simple, a simple statement. And we want to minimize our building electricity costs over time such that the building remains comfortable for its occupants. That's it. We want to save building owner money, and we want our building occupants to remain comfortable. And so what do we have to think about there in terms of a model? Basically, we can divide all of the activities and systems in our building into two buckets, and we can have controlled systems, which will optimize with our model, and we'll have uncontrolled systems, which may impact and contribute to those comfort conditions, but we have really no control over them. And so for controlled systems, in the model that I'm going to share today, those controlled systems are heating, cooling, ventilation, and lighting. So we're talking about thermal comfort, and we're talking about visual comfort. Uncontrolled, we have a tremendous load from miscellaneous equipment, sometimes as much as 30% of an entire building is miscellaneous electric loads. And then, of course, our occupants are uncontrolled, but they're really a heat generating load. People generate heat in the building that must be addressed with space conditioning. So we've developed a model that looks at those four systems and essentially creates optimal operating schedules for a 24-hour period for the building. And those operating schedules are based on two factors, two predictors, basically outdoor temperature and building occupancy. So we're predicting and creating optimal heating, cooling, and ventilation schedules based on outdoor temperature and building occupancy. And so how do we do that? We all know heat flows are definitely not linear, but we have a linear program. So one of the first things we do is essentially estimate all those nonlinear processes with piecewise linear functions. And so this is where we turn one heat flow process from an HVAC, from a heating unit, for example, now becomes perhaps a dozen or more functions depending on the outdoor temperature. And so we've created this set of decision variables where we're deciding how much heat gain or loss the building's going to experience based on outdoor temperature and the building occupancy. And there's a number of different predictor variables we could use. Those are the two that we are modeling on to initialize this system. So the real-time condition part. So I mentioned it briefly in the beginning. Real-time conditions for this work is basically looking at real-time pricing and weather. So here in California, not yet, but we will have accessibility to a real-time pricing signal. And real-time pricing is based essentially on the wholesale electricity market. And so you're getting prices every 5 minutes that are going to be different. And those prices can either, you can either take them in one or two flavors. So we have day ahead real-time pricing, where a customer is notified of the prices they're going to have for the next day, usually around 4 p.m. in the afternoon, and they can take that information and then schedule their business equipment use or schedule their energy consuming devices around that schedule. This is less risky to the customer, but it is also less, there's less benefit ultimately in it because they're unable to capture the actual variability in the electricity markets. And so the second type of real-time pricing with this model is based on is essentially based on what's called spot prices, which are 5-minute electricity prices that are being broadcast continuously by the utility. And customers don't know the price exactly in advance. They're applied to a customer's bill at the end of each hour. So, but they are fairly predictable, and they coincide, high prices tend to coincide with periods of increased demand, for example, and low prices with low demand. And so you can see on this chart here for real-time conditions, if you can access 24 hours of 5-minute data for your electricity prices, you can do something like avoid that peak in electricity cost up around 9 or 10 cents a kilowatt hour in the red circle. You can avoid that and plan for it, and even plan for using electricity, doing all of your work, running your building, doing what you need to do when the electricity is actually negative. You'll be paid to use electricity. And you can see in this graph, there is a period of time late at night, 2 a.m. to 4 a.m., where a building would actually be making money on the real-time price if they were to use energy. And so it's that diversity and that variability in the real-time pricing that makes optimization of building operations such an enticing idea and something to think about and start looking forward to. And that's enabled by a couple of things. It's enabled by building automation systems. So we need a system, a brain in our building that's smart enough to be able to house the optimization module and to be able to then send out optimal schedules to all of the end-use devices in the building. So the advent of building automation systems has really made this a plausible idea to think about. The second is, and really related very closely, is the increase in computing speed. So when we have millions of variables and millions of constraints, and these systems are so large, even for the fastest computers, sometimes finding a reasonable solution is not guaranteed, let alone an optimal one. So as computer speeds have increased dramatically and buildings have gone to building automation systems, we now sort of have the infrastructure in place to start optimizing our operations around things like cost or energy use. And so for this model, it's a fully automated model, and it goes out and it pulls information from the web like you would expect. We can pull a 24-hour weather forecast. Weather.gov has an API you can access quite easily, and you can get hourly temperature and sky conditions, both of which you can see here. You can get humidity, you can get alerts, you can get a whole host of things, but we can pull that weather information and we can go out to our utility and we can pull the 5-minute data from either the day ahead market that's been posted, or we can estimate it based on yesterday's price or last year's price or an average of those two prices. And so we can predict what the 5-minute price is going to be for the next 24 hours. And this data comes from a utility out of Chicago that has a publicly accessible API as well, and you can access their utility cost information for your purposes. And so we're looking at temperatures and electricity data for sort of the Midwestern region of the United States. So just keep that in mind. So we can take all this in and create this model. And I believe the model we have is fairly small. It's got about 70,000 or 80,000 variables in it to look at each of 276 time periods. So that's a 5-minute time period over 24 hours. To look at that and think about how can we control the heating, the lighting, the cooling, and the ventilation to keep our temperature within range, to keep our lights on in a way that people need, use normal schedules for occupancy, and control those systems in an optimal way. And so in doing that, you really can capture some significant savings. And so in this slide, you can see there's 2 charts. The chart on the top is showing the schedules, the optimal schedule for one example building. And I know it's a little hard to read, but we have our heating system, we have our cooling system, we have lighting, and we have ventilation. We have 3 essentially levels of heating, 2 of cooling. The ventilation you can see is the purple, sort of the purple line there at the bottom that's running when the heating or the cooling's not on. We need fresh air circulating, so it comes on to circulate appropriately. Lighting is the solid yellow line that you can see in that little top graph that steps down over time. This simulation I ran yesterday morning, so it was for Thursday for 24 hours, starting I think around 9 o'clock. And you can see over time, then in the bottom graph, the outdoor temperature is the orange line. The outdoor temperature is going to peak for us here in the Midwest at about 75. This was yesterday. We'll drop down to below 50 last night, and then it starts to climb again. And the blue line is showing the estimated indoor temperature of the building under these optimal operating schedules. And for this model, I had a fairly broad comfort range for my system. I said, you know, keep the building between 68 and 75 degrees because I wanted it to solve quickly and get some data for this presentation. But you could tighten those down. You could do things like add deadbands for a heating and cooling system, you know, times when the system wouldn't run, things like that. So over time, you have this schedule that then you can implement to reduce your costs using those estimated prices. And so as a comparison, and we'll get to some of the savings numbers, I know I'm running out of time, at the end, on the top is optimized operation, on the bottom is baseline. Baseline and an optimal don't really look that different. For a baseline, we had a temperature set point of 72 degrees and the thermostat was set there and the building was operated with a fixed lighting schedule and a thermostat set point of 72. And it for the most part, keeps the building fairly constant. The optimized operation, as I said, had a wider band of temperature, and you can see had a little less variability. But during the hot parts of the day there on the left, where the temperature is highest, you can see quite a bit of variation as the temperature fluctuates up and down with those cooling systems working more often than they are in the middle of the night, sort of over towards the right-hand side there where there's some flatter lines and a little less operation. So overall, these systems, you can do things then like take the history of the building. And instead of trying to estimate, you're continuously collecting information using sensors and data loggers to collect temperature and status of your equipment. You can really fine tune these kinds of models using actual data that's going to learn the real operation and the real performance of your building over time. So we start with a model that may work. You know, all models are wrong, as I'm always told. Some are useful. We start with a model that works, and then over time tweak it with real data from our building to really fine tune and have the algorithm learn, so to speak, the way that your building operates. And so these things become more accurate over time. But even for a very basic type of example, here you can see, and I just wanted to point this out so you can see some of the things that an optimal schedule is doing. On the top, you have the baseline, and that blue dashed line is essentially your cooling system operating on high because it's trying to keep your building around 72 degrees. And then at the bottom, for the same period, this was about 2 to 9 p.m. Yesterday's data, we see that it's more of an intermittent low cool, the green dashed line. And that's because if you look in the shaded area of that 5-minute pricing, you'll notice that in the yellow shaded area, the prices during that time, we have 0.57, 0.4, 0.8. Those are, sometimes twice as more expensive than the time leading up to or the time right after those time periods. And so when we do something like a baseline running our cooling system constantly, we're ignoring the fact that our electricity price just jumped twofold or just doubled. Whereas the optimal schedule is using a intermittent approach to avoid running those systems during those times when electricity is more than twice what it was in the previous period or the period after. And again, there's 276 decisions, so to speak, 276 time periods that need to be made for each system you're controlling. So I couldn't really show you the entire all of the decisions that are going on. I just wanted to show some of the detail here as one example. But over time, this has the potential for significant savings. And so we did a small base case. We looked at a 5,000 square foot building, a typical office occupancy. We had a max occupancy of about 34 people. We added in our miscellaneous electric loads at about 2.3 watts per square foot. We looked at lighting, nice efficient LED lighting at 0.5 watts a square foot. We had 20 to 30 R value insulation in the envelope. We looked at air change outs due to infiltration and exfiltration of about 1/2 a complete volume per hour. And the optimal schedule, looking just at those 5-minute costs, and we haven't even talked about demand, which is a whole nother set of optimization that's going on as well that I just am not going to have time for. But just for the real-time price optimization, we got 26% savings. And that's in costs. Those are dollars in pockets for building owners. And we are moving electricity use around, but we still have energy savings. We got about 16% energy savings for that time period. On average, for this very small building, 5,000 square feet, might be a small tenant space, for example, we're putting $1,200 for this particular scenario and this particular utility rate structure back into the pockets of building owners. So over time, these things can add up significantly. And when you think about demand charges, which I wish I had time for, but I don't, is another 30% on top of your monthly, is about 30% of your monthly bill. Optimizing and reducing your peak to account for demand adds significantly more savings. So takeaway, significant savings coming out of the commercial building sector when we start looking at optimization and model predictive control. It's not everywhere now, and it probably won't be everywhere tomorrow, but the potential is there. And with things like the demand standards in California that are due out next year and real-time pricing that's being more broadly adopted, it's going to become a significant tool for saving money and energy and carbon for our building sector going forward. So thank you. And I know I used a bunch of time, but questions?
Excellent. Yeah, if you have time, folks, stick around and ask. Cori's here for some questions. And we'll have to get you back, obviously, to do the demand demand presentation, the demand side.
Yes, another 20 minutes just to talk about demand.
I know it's hard to do some of these topics in like 20 minutes. It makes it very challenging.
Absolutely.
Feel free to raise your hand if you have a question, or put it in the chat and we will get it answered.
I'll take it that it was so well, there was no questions. Let's see.
Oh, we're getting claps. You're getting claps. Here we go.
Oh, yay. Thank you.
I was, so this is Subrajit here again. I was wondering, I'm pretty new to this model predictive control too, but I've been hearing it quite a bit. I was wondering, you know, like what tool or like, you know, the model predicts the algorithm that you discussed in the beginning is running a model and kind of predicting the energy use. So
right.
So the like the model has to be pretty good, right? With like it should incorporate all the 4 systems like heating, cooling, ventilation, and lighting.
Correct.
Yeah. So I was wondering what tool do you use to kind of model all that in? So
the code itself is written in Python, which uses an open source optimization engine called coeration by default. So there's lots of tools out there for optimization. Cplex is well known. This one, coeration, I actually just learned about this doing some recent work on the algorithm. But overall, everything's coded in Python currently. Long term, it would be become part of a building automation system routine that would then be used to control the different systems in the building.
Oh, okay, yeah. So
did that answer the program? That answer the question?
Yeah, I was more so on the like the model that is running, let's say the HVAC system and like, you know, how the HVAC system responds. That's also in that Python program.
So the physical implementation of this model has yet to be done. So is that more what you're asking, is what kinds of equipment or things are we using in the building to actually do this control?
No, I was more so on like, you know, I thought the algorithm is running in Python, but it is running another model. Like I know that like some groups do like use dynamic modeling like Dymola or something like that to run the model. So
yeah, it's coeration. So there's a whole package in Python called Pulp, and it has some default optimization engines and default linear programming routines that includes a pre-configured instance of coeration, which is the optimization routine. And I don't know the exact algorithms that Coin is using to solve the problem. Probably many and a lot of different tools on top of that to make it run more quickly. But I do know that the program itself is called coeration.
Okay, thank you. Yeah, that's all.
Yep.
Yeah.
Great. Any other questions? I had a quick question, Cori. I was wondering, so the optimization really requires having, you know, building automation in the different systems. So for new buildings, it seems like that could be, you know, pretty more easily done than maybe retrofitting, or I don't know. Is there any thought about how to integrate all those systems? I guess you could have one system in, but it helps to have the whole building, right? All the systems automated.
Well, the systems that we looked at constitute about 70 to 75% of the load of the building, which is a good example. I call it whole building control. It's not the whole building. We're not doing things like controlling plug loads and miscellaneous processes. We're not controlling refrigeration if that exists. So there's some things where we just, it's impractical to look at it. But new buildings, absolutely. If you can have a building automation system with the intelligence and the speed and the memory capacity to be able to run this kind of model, that's ideal. In existing buildings, that's when I turn to my team at CLTC, and they're doing a lot of work from the hardware perspective. How do we physically integrate actual building systems using components that we can get today? And so there are system integrators out there, hardware components that you can purchase and that speak multiple building languages. So you can then tie together all of these different systems to one central piece of hardware for control with a model predictive control, or for any other type of sort of centralized control strategy that you might want to implement.